So public keys are known by everyone. Private keys are only known by you. So here's where we get to the fun encrypting part. Now that we know all these variables, what we do is we write out a message. So we're gonna use screen. We're gonna encrypt the word screen. Okay. So what we do is we convert each individual letter into a number, and for simplicity, we're gonna just have it equivalent to what it is, in the alphabet. So S is equal to 19 because it's the 19th letter. Okay? So when you do that for every single letter, all right, we get M. So M is equal to 19. You have to do this for each letter, by the way. So you encrypt M. Yeah, you encrypt the different values of M separately. So you're going to encrypt S and C and R and E and N. You're going to encrypt them completely separately. Okay? So, doing this, so we're going to encrypt 19. Okay? So, we're going to make K our encrypted number. Okay? So, K is equal to M to our exponent, and then we're going to have modular division for N. So essentially, it's our encrypted letter to the third, and then it's going to have modular division by our public key, which is 33. So for the letter S, it's going to be 19 to the third, modular division by 33. Okay? What that gives us is a remainder of 28. So that's the first letter. And you go through and you do that for every single letter or character that you have in your message. So for screen, we have 28, 27, 24, 26, 26, and 5. That's what we come up with. So yeah, so that's it. To decrypt it, what we do is another equation. It's M equals K, which is our encrypted letter, to the private key value, and then we have modular division by the public key again. So in this case, it's going to be 28 to the 7th. It's going to be 28 to the 7th, and then it's going to be modular division by 33. And that returns the value that you originally started with, which is 19. So there are some important things that need to be remembered. Even though there are multiple values of D that can satisfy the equation that D has to have a remainder of 1. So it's D times the exponent modular division phi of n. It has to be an integer, or else it's not going to work. And also, your public key, again, I'm going to say this, it has to be the value of your public key, which is in our case 33. It has to be bigger than the value of the letters. So if you want a really secure message, you're going to make your letters really big. So like S is going to be 20,000 or 20,572. But you just have to keep in mind that your public key has to be bigger than that. And to get a public key really big, you're going to need really big prime numbers, and big primes and a big public key is going to result in a really big private key. And when you're decrypting, you're going to take whatever your big encrypted number is, and you're going to raise it to the power of your really big private key, and it's just going to be really massive. So odds are you probably can't do too big of a public key on paper, and even in Excel, you can't do you can't have 5 times 11. It's too big, and Excel really freaks out with that. So that is the basis for RSA. That's how RSA works.